Hello, everybody. It's time now to start into a brand new topic. We just went through a whole bunch of interpolation methods. We talked about Lagrange interpolants, and we talked about Hermite, we talked about Newton polynomials, we talked about cubic splines, and some different things like that. Make sure that you're caught up with those things. But we're going to turn the page and start talking about something new. We're going to start bringing in some calculus concepts, and it's all going to start with how we process the idea of a derivative um, in terms of like approximations, in terms of maybe how a computer might handle it, some different kinds of things. And then once we've got those definitions, we're going to be using those for more advanced kinds of things. We're going to be talking about some related topics that use derivatives, like gradient descent, like solving differential equations numerically, and maybe a couple of other things too. So that's the next path for the next couple of weeks that we're going to be on. It's maybe a little bit challenging at some parts, but it starts off pretty simple, and I think that you're going to find that this first lecture is not bad at all. So why don't we get started and begin with this. So finite difference approximations to the derivative. That's what we're talking about here. And so let's just fill in the blanks and see how it unfolds. So sometimes for practical applications, we may want to utilize the concept of a derivative, even when we cannot truly do this. Kind of strange wording there, but there are a couple of reasons why I use that wording because, well, let's see. Perhaps we're working with a programming language where we need calculus to solve a certain application, but gosh, that's not embedded into the language, right? Maybe you don't have a math package or access to one, right, that has any calculus functionality. And I mean, even if you did, how do some of the existing math packages work? A lot of languages do have such packages, but what are they using when it comes to things like calculating a derivative, that sort of thing? Well, this is kind of what this chapter is going to get into. Another thing that can come up is that for modeling applications, this is pretty common. You might require calculus concepts, but we only have discrete data points rather than continuous data to work with. So that means, right, if you think about it, the definition of the derivative requires us to be able to take a limit and get in as close as possible. But maybe we can only take measurements at certain points of time. So we don't have continuous data. Well, therefore we can't define a derivative properly, but maybe we can find a way to estimate what the derivative would be if there was a continuous function going through those points. Something like that. So there are a few different simple reasons why we might be interested in a topic of approximating derivatives or using these schemes for what we call numerical differentiation. These schemes are about as hard to come up with as digging out your old calculus notes because they really aren't that tough. They will look very, very familiar, and we're going to see what they look like in the next page. So let's jump to it. The most basic formulas for numerical differentiation are exactly what you might expect. Derivatives are slopes, right? And so it stands to reason that the best estimates for, the slope of a tangent might be some other slopes, like slopes of secant lines. That might be, represent small steps forward and a change in the height over the change in a rise over run sort of thing. And that's really where it comes from. Let's recall what the derivative of a function f of x is given by. So this is what it is. This is the first principles definition of the derivative. This should be familiar. Even if it's been a little while, I'm sure that you'll remember, right? This is just the difference in y's over the difference in x's. And that difference is getting very, very, very small. So this is the limit of the slopes of the secant lines. And if that limit exists, you have a derivative. That's like all of first year calculus. That's what everything hinges on. Okay. But what this does, what our numerical differentiation schemes do, is they treat the h as a small positive value. We'll call it the step size. One word or two, I don't really care, whatever. Rather than letting it approach zero. Okay, that letting it approach zero requires a lot more, some you talk about limits in first year, and there are formal definitions to really treat this rigorously, but that's hard to feed a computer. And then there are like intuitive limits, which regard like if we know enough about these functions, we can kind of deduce what the function should be doing as it gets in really, really close in order to calculate those limits. But we don't have those tools at the ready in general. So instead, we're going to keep the h as some small positive value, non-zero. And the idea is that if h is small, maybe the related slope of that secant line is pretty close to the slope of the tangent line that we're actually looking for that represents the derivative. Okay, so using this, we can define a few different kinds of derivative approximations, each of which can be useful in different sorts of situations. So the very simplest, finite difference approximation at a point x0 involves a formula that looks very much the same but doesn't have a limit. So it's going to take the height of the function at x0, the height of the function at x0 plus a little step forward, and divide by that small step size. So this is nothing more than a secant line connecting x0, f of x0, and x0 plus h, f of x0 plus h. And that should seem like it makes a lot of sense to start with as a formula. Okay, the backwards. Oh, this is a finite difference approximation. This blank was supposed to be the forward difference approximation. It's a forward difference. It is a finite difference approximation, but it's a forward difference approximation because we're taking a step forward, x0 plus h, to get to a nearby estimate, essentially, or a nearby sampling of what the function's doing there. And then similarly, we have a backwards difference approximation, or backward. I don't know whether it's in backwards or backward. I don't really care. And that's very, very similar. It just uses the x0 as here, and then we step back to x0 minus h and evaluate the function there. So you see, it's the same sort of thing. This is still a difference in y's. So this is a difference in y's over a difference in x. And that was true up here, but it's also true down here, right? It's just a matter of seeing what is the current value that I'm treating as? Am I stepping forward or backward? I can get different kinds of samplings for what the derivative is, different kinds of estimates based on whether I step forward a little bit or step backward a little bit, and maybe for some applications one is better, and maybe for the other one could be useful in other circumstances, that sort of thing. But both of these provide us with estimates of what's happening with the derivative. Okay. So graphs are everything for me. I think that it makes a lot of sense if we just draw a quick graph and see for ourselves. So if we have a function, I'll try to draw the same kind of function. Let's draw it like this. And let's draw something similar here. Okay. And I'll choose an x0, say right here. And I'll choose an x0 right here. Same sort of thing. What we're doing, the true slope is the slope of the tangent, right? This is the true derivative. So the true f prime at x0 is the slope of the tangent line at x0. Okay, that's true here too. This is the true value that we're looking for is the slope of this dotted green line that I'm drawing. Okay, so ditto. The difference is, how are we going to estimate this thing? Well, let's take a look. For the forward, so if I write forward difference approximation versus backward difference approximation, what essentially I'm doing is taking a nearby point, and let's use a slightly different color maybe. Maybe this is it. Maybe this is a big step, but x0 plus h is right here. I'm taking this point and that point, and essentially Well, I would like the same color actually, so I'm gonna just change this to this orangey color I've got. Okay, so that's what that is. I'm gonna say the slope of this secant line approximates. Sorry for the like kind of ugly looking text here, but approximates the true derivative. Okay, so that's what this orange line, that orange straight line that's right there, approximates that green line that is meant to be the true slope. I don't know why I didn't use the straight line tool before, but the difference is for backward difference approximation, where I evaluate the, the other point is going to be behind x0 instead. So it's just that x0 minus h is what we use. And so the estimate is going to be the one that goes through this point right here and this point right here. And in this case, it looks like it's going to underestimate the slope because it's a little bit milder than the true, right? So I'll say same here. And really, it's just asking, where do you want the that step to be? A small step forward, a small step backward, and maybe I get a better estimate of the slope for certain functions than for others, depending on what the function is. Cool. So each can be useful in different ways. You'll see that in an example before the end of this lecture as well. There's one other commonly used scheme, and in fact, it's more useful in some certain circumstances, and it is the centered difference approximation at x0. And what's interesting about the centered difference approximation at x0, it's still a difference in height, a difference in y over a difference in x. Difference in y over difference in x. Except interestingly, it kind of, it doesn't involve the function being sampled at the point you're interested in at all, which is kind of interesting. But then I want you to think about it. If you look above to those two examples, it looks like the first example, that forward difference approximation, is going to produce a steeper slope than we want, right? It's going to be an overestimate for the true derivative. While the backward difference approximation, it looks like it's going to underestimate. We get a milder slope than we might want. And perhaps if we used a data point ahead and a data point behind, we could mitigate that. And we're actually going to see that there, on average, is less error associated with a centered difference approximation. So that's what you're doing. You're taking a step forward here minus a step backward. So you're comparing those y values, but then you have to divide by, well, 2h. 2 times the step because you're taking a step forward and a step backward and comparing those. So this is what the centered difference approximation looks like. CDA scheme is right here. And let's draw that out to see how that's going to look. So I'm going to do the same sort of graph and we'll see. So wait, what the hell did that look like? Sorry. It went up like this, kind of exponentially. I didn't like that. Whatever, it's fine. And I'll put x0 right here. And for the centered difference approximation, we're going to take a step forward, x0 plus h. We're going to take a step backward, x0 minus h, and we're going to compare those points and find the slope of that secant line. Here would be that secant line slope right there, that straight orange line right there, versus the one that we're looking for, which actually, the way I've drawn it, you can see looks like it's a very close approximation in this case. So I'll write that down here. The orange line seems to have a much closer slope to the orange line. Okay, so we got 3 different schemes, and you can kind of see how they work right here. We have the forward, the backward, and the centered difference approximations. We're going to use these on a couple of examples. That's going to finish off this lecture. And then we're going to do a little bit more careful analysis for schemes and the error involved in using them and so on. And that's going to form the next lecture, which honestly is a little bit more interesting, but probably more challenging at the same time. I think it's good to have this lecture first so we understand what's going on and we know what this is useful for, and we can see the numbers at work. But hopefully these graphs are helpful to kind of showcase that. So 2 examples to get through, and I've done some of the calculations off to the side. We have let f of x equal the cubed root of x. We want to find forward, backward, and centered difference approximations for f prime of 8, considering a step size of 0.5. Okay, so a couple things. H equals 0.5. We've got a function right up here. And what we're trying to do here is, well, imagine that we don't have access to compute the derivative. You know, this is a simple enough example that obviously you could probably do that by hand and program that into a machine and so on, but you understand that maybe you have a function that is much more complicated than this in practice. So it's nice to be able to formulate something and calculate based on that. So, okay, let's work on each of these schemes. So the forward difference approximation with h equals 0.5, and we're dealing with f prime of 8. So f prime of 8 is going to be approximately equal to, and the scheme is going to take a half a step forward. So we're going to look at f of 8.5 minus f of 8 over 0.5, just like that. All right, you can calculate this no problem. If you do, well, I mean, it's the cubed root of 8.5 minus the cubed root of 8 all over a half. And if you work this out, I did it to a bunch of decimal places. It's not really the point to worry about this right now, but with a forward difference approximation scheme, we get about 0.0816551. Okay, we're going to do the same thing with backward and centered, and then I just want to talk about it a little bit in terms of the graph of this function, because I think that it is very, it showcases, it helps you to see kind of what's going on, why we get overestimates, underestimates, and stuff like that. So f prime of 8 for backward difference approximation is going to be f of 8 minus f of 7.5 over that h value of 0.5. And so this is nothing more than the cubed root of 8 minus the cubed root of 7.5. Dividing that by 0.5 is the same as multiplying the answer by 2. But you end up with 0.085132359. I took a bunch because I wanted to get to something, I don't know. I don't care if you stop it after 0.0851. That's fine by me. Don't obsess too much about that. Give me a little bit of precision, but I'd rather you spend your time worrying about concepts rather than the intricacies of how many decimal points I want. Unless I'm specifically asking about like 3-digit math or whatever, then we'll worry about that. For centered, we have f prime of 8 is approximately equal to, and this one goes a step forward minus a step backward over 2 times the step size, like that. And so if you work that out, we end up with 0.08339,373, like that. Okay, so we get estimates in every single case, just over 0.08 or so. For this example, we can actually calculate the truth. So the true value is given by, well, check this out. If we have, this was the cubed root of x, so we know what the derivative is, for heaven's sakes. F prime of x is equal to a third x to the minus 2/3. Okay, so f prime at 8 is equal to 1 over 3 times 8 to the 2/3. 8 to the 2/3 is, cubed root of 8 is 2, squared is 4, 4 times 3 is 12, so it's 1 over 12 is what it should be. So equals 1 over 12, or 0.08333 onward and forever. So this here is something we can actually calculate here. So we can see for ourselves that it looks like our estimates are pretty good. You know, they're not exact, and that's okay. But I want to use this to kind of showcase some things. I can draw this function. We should know what the cubed root of x looks like by now. If not, I'll remind you. I don't have a lot of room here, so I'll just kind of scroll in the side. But check this out, right? If we have this function that looks like this, and cubed root of x comes up, is like vertical tangent for 1 split second, and then moves on its way. See how the slopes are getting milder and milder and milder as the function continues onward. So if you're trying to estimate the slope right here, and you take a step backward to estimate versus a step forward to estimate, well, see, because the slopes are getting milder and milder and milder, if you take a step forward to use that estimate, you're going to get a lower answer than the true value, right? The true value is the one that happens right there. That's the tangent slope. That's this slope right here. But this is going to be bending away from that line. And so if I take only a step forward to estimate, I'm necessarily going to get an underestimate for the true slope. And same thing if I'm looking backward, I'm necessarily going to get an overestimate for the true slope. So see, like depending on which approximation I take, it's kind of predictable what's going to happen. You can see that in our answers. In this case, we can see that the center difference is the best choice. But there's some cases, depending on how the function's changing, how quickly it's changing, what our step size is, that can really, really influence which of these does the best job. And again, we're going to talk more about error and how much we can expect to be off and so on in our next video. All right, before we move on, I have one more example I want to talk about here, and that is this problem of using nodes. We talked at the very start about how a challenge can be estimating a derivative when you don't even have continuous data. Here we had y equals x to the 1/3. Maybe you just have a bunch of measurements, but for some application, maybe you've got a differential equations model that requires you to know something about the derivative, but all you have are some measurements of data, and you need to know what the derivative of that is. Well, you have to be able to find a way to estimate what that is, given just like a few heights that you've plotted. So difference approximations give us a way to do as well as we can, given that discrete data. So for this, I'll assume for a second that your nodes are evenly spaced, but you don't have to. You just have different h values, right? If the difference in x's between each node is different, you can just use kind of a different h for each one. But here we'll just define in general a constant h, so they're evenly spaced nodes, and that h is the difference between any two consecutive x values. So here's what I'm talking about. Given nodal data, and we have 3 points here, 0, 4, 0.13, and 0.26. So, right, if I was doing some measurements, maybe I was measuring, I don't know, temperature of something at given periods of time over the span of seconds. Maybe I'm measuring luminosity of some, right? Like it could be anything. It doesn't really matter. But I have measurements that are taken at x equals 0, x equals 0.1, and x equals 0.2. So the only data I really have are this, 0 and 4, something up here, 0.1 and 3. So if this is 0.1, I've come down a quarter of the way, and 0.26. So I've gone up 4, 5, 6, right about there. This is the data that I have, and I'm asking you to estimate a derivative. You see what the issue is, right? Like I don't have the ability to take limits and all that kind of stuff. But what I can do is use the idea of, well, I can estimate a slope by using 2 consecutive pieces of information. And here's what we're going to do. We're going to calculate the forward difference approximation at x equals 0, the backward difference approximation at x equals 0.2, and all 3 of them at the middle node, 0.1. Okay, so let's do that. And we're going to see that it's not too bad. So the forward difference approximation at x equals 0. Put a little cloud around this, and then we'll do some calculations. This is going to equal, I want to take the y value here and the y value there, subtract them, difference in y's, and then put them over that h value, 0.1. So this is going to be, what were they? There were 3 minus 4. So 3 minus 4 over the h value we said was 0.1. And that looks like we're going to get minus 1 over 0.1 is negative 10. So that is the estimate on what the slope is. Really, it doesn't look like the slope here is minus 10, but then think about it, the scale, right? Like the x value is just going by tenths, and the y scale is already going up by like whole numbers. This is 4 up here, right? So it makes perfect sense when you think about it. Okay, cool. The backward difference approximation at x equals 0.2. Well, the backwards difference approximation at x equals 0.2 is going to take this as x0. This is x0 minus h, right? So we're taking a step back, and we're comparing those two things. So we're going to take the difference in y's, and that's going to be 6 minus 3, and put that over the h, 0.1. I think that works out to 30 if you do the math. And you can see, right, it is a positive value. The slope is positive between those 2 points. So that should make some sense as well. Okay, I want to pause for a second before I do the last one. Notice that because there is a first node and a last node, not all of these approximations are well defined for all three of them, right? At 0, I can only define a forward difference approximation. It doesn't make any sense to talk about a backward difference approximation because nothing happened before 0. I have no measurement there. It's not well defined. Similarly, at 0.2, it makes no sense to talk about a forward difference approximation because that's when time's done. There's no 0.3 measurement. So forget about that. We don't have that. It only makes sense at 0.2 to talk about a backward difference approximation given the data that we have. But at the middle one, you have options. So at that middle one, so at x equals 0.1, we have, and we'll do all three of them. So let's do the forward, the backward, and the centered. And by virtue of how these things are defined, we've actually already done 2 of these. I want you to think about this for a second. The forward difference approximation at the center node, this one right here, is going to be the one that steps forward. It's going to take a difference in these y's and put it over a difference in these x's, right? We've already done that. It's the same as the backward difference approximation for 0.2. It used the exact same data, so we should get the same answer, right? The forward difference approximation is going to be exactly the same thing as the backward difference approximation before. It's the height at 0.2 minus the height at 0.1 over that 0.1, right? So yeah, essentially is doing, I was going to write down the formula here and I was like, it's a silly thing to do because it's exactly the same as this one here. I just want you to see that and understand that, okay? If that doesn't make sense, talk to me. If you do, of course, you get the same thing, you get 30. And same thing, the backward difference approximation at the middle node is going to be the one that compares the data here with the data there. And it's going to be the exact same as the forward difference approximation from the first node. So it should be the same results. It's going to be the 3 minus the 4 over the 0.1. And that gives us the minus 10 again. The one that's different is going to be the centered difference approximation at the center node. Because that's going to be the one that doesn't even look at the center node data. It looks at what's happening around it. It looks at this one and that one. And tries to make an estimate of what the derivative would be at 0.1 using only that data, which is weird, but check this out. If I do that, let me see. The last one was, I need to get the data, it was 6 and 4 were those y values. So it's going to be 6 minus 4 over 2 times that h value. So it's 2 divided by 0.2, and I think that's 10. Okay. Looking back to our graph, imagine you were trying to, say, interpolate this with some sort of function. Right? I don't know that that's what it looks like, but it could be what it looks like. Maybe it's more complicated than that. Maybe, it doesn't change so smoothly. I don't really know. But this is the best that we can do, maybe. And you can see that the derivative here looks like maybe it should be small and positive, or it could be, right? You can see the large positive slope here. You can see the somewhat small positive slope right there. It's the best that we can do to approximate those derivatives given the data that we have. And it's reflected in some of these estimates. And you can see it if you chart it out. It should make some sense. So yeah, basically, that's it on the surface. And so from here, I want to bring it in and talk a little bit about where we're going to go with this. So it's great and all to have formulas, and I think these are pretty easy to use. But it's nice to be able to connect these to the idea of like that some might do better than others, that some might be more prone to error than others, and some might have their error decrease more quickly as that step size decreases. And we're going to take a closer look at that next lecture. And I think that there's some pretty interesting little derivations and proofs there. So I hope you'll bring your brain and as well as your attention, and we should have a good time with it together. So until then, I wish you all a fond farewell. Ciao for now, and see you in the next lecture.